Dear students, I have decided to offer an online tutorial how to implement the corresponding tests that I discussed in the lecture in Eviews. Eviews is a standard econometric software which is very powerful, and you can basically run single or simple multiple equation models in Eviews. I assume that you are familiar with Eviews from econometric classes because this should be a standard program, and I'm sure that you can somehow acquire this program or at least get access to this program. At least at campus, you should have access to the program with your credentials. And anyways, I assume that you somehow manage by yourself to get access to this program, which is very standard use in statistics and econometrics. So basically, if you open Eviews, this is what comes up. Now, this screen here, this workspace. So first, what we want to do is we want to implement the GRS test. Yeah, you remember it's the left-hand side testing approach where you have certain test assets sorted by certain characteristics, and you want to test the intercept terms if they are statistically significant. Under the null hypothesis, the asset pricing model, which is on the right-hand side, which basically are which are used as the regressors or as the independent variables in our model. Under the null hypothesis, we assume that this model can price our test assets correctly. Yeah? In this case, the GRS test would give us the result that or the test statistic would indicate that the GRS test is statistically not different from zero, yeah, implying that the pricing errors are basically not different from zeros. In this case, obviously, we would assume that this pricing model works correctly. If the GRS test suggests that our pricing models are significant, in this case, we would reject the pricing model because it cannot price these test assets correctly. So how do we proceed? Okay, let's go here on File, New, Work File. We open a new work file, and now we need to know the frequency. So we go on unstructured up undated, but we have to know how many observations we have. So let's go on to our Eview, to our Excel file. This is our Excel file that I will upload for you in Moodle. So what you see here is here are 25 portfolios, yeah, 25 portfolios from denoted as P1 until P25, yeah, and we have how many observations we have on column A gives us the time series. So we have 625 minus 1, so 624 observations ending in June 2015. Okay, our test assets are 25 portfolios sorted by size and investment. And now it's important to know these are assets or test portfolios already in excess form, which means I have already subtracted from each return the corresponding risk-free rate at time t. Yeah? So all these assets here are provided in excess form. Okay, so 624 is the number of observations. So again, we go on File, New, Work File, dated, unstructured, and undated, observations 624. Push the OK button, and this next wizard here opens. So now we have now created like a new workspace here, and now we go on Proc, Import file from. And now we have to know where we have located the file that we want to operate with. I have located it on the desktop already. Just for illustration, it's denoted as data 25 portfolios sorted by size and investment. Double click and Eviews will upload this data. Just push the finish button, and here a wizard opens, asks us link important series and other objects to external source. We don't need that. Push no, and so voila, we are ready. We have uploaded our test assets into the system. Okay, here in date if we double click date, it just gives us the vector of time series observations, so basically of the months that we have in our sample, starting in July 63 until June 2015. Okay, we can delete this vector because we don't need it. Delete it. Yes. So now we are left with our 25 portfolios. Okay, starting with P1. P1 is a portfolio which consists of small stocks and having a aggressive investment style. Yeah. So what we also need is we need the risk factors. We go again on proc. We have to upload the risk factors, import file from, and of course this matrix I have stored as well on the desktop. Here we find it, data, Fama and French 5 factors, double click, and it is uploaded. Push the finish button directly, and here again no, and Eviews uploads the data set. So what we have is here CMA is the investment factor, conservative minus aggressive investing stocks. Then we have the date. We can delete it. We don't need it. When you check the Excel file, you will see that the dates are exactly congruent. So of course this is necessary. We have to have the same dates, obviously, the same date structure for the regressor matrix and the dependent variables. Okay, so HML is the value factor, high minus low book to market ratio. MKT underscore RF is the market excess factor, or the market factor in excess form. Actually, we can rename it. Let's rename this as MRF, okay, which is the market factor, because in the code that I've given to you, you will see that the code basically treats or denotes the market excess factor as MRF. So let's do it here also correctly as MRF, as the market factor in excess form. What else do we have? We have here the risk-free rate. Actually, we don't need it here in this application because we have already the portfolios in excess form. Moreover, we have RMW, which means robust minus weak firms, which means these are firms, obviously, or this is a portfolio of stocks that invests in stocks and companies that have a high profitability and finances this position by shorting stocks that have a low or a weak profitability. Okay, so this is the profitability factor. Then S&B, as we know, the size factor, small minus big stocks. So these are our zero cost portfolios. Okay, so first of all, we want to implement the left-hand side approach. We want to implement the GRS test. Yeah. So what we do is we go on objects, new object, and now okay, let's first implement a single equation. How would we do that? Let's say we want to know if the first test asset, the first portfolio, can be explained by the Fama and French 6-factor model. Okay, so how would we do that? We would go on equation, okay. So by default, the method here is least squares or ordinary least squares. So we would put in P1, which are the excess returns of our first portfolio. This is a vector, okay? Then empty space, C, which is by default, Eviews recognizes this as a constant term or as the intercept term. Then again, we leave a space. And then we have as regressor matrix RMF, which is the market factor in excess form, SMB, which is the size factor, HML, value factor. We have RMW, which is the profitability factor. We have CMA as the investment factor. And last but not least, we have OMD. No, sorry, we have OMOM, right? No, we don't have the momentum factor here in our data set as I see. So we are operating, okay, our data set does not contain the momentum factors. Our data set contains only the risk factors for the Fama and French 5-factor model. So the market factor, size factor, value factor, profitability factor, and the investment factor. Okay, so now we regress the P1 on an intercept term and these 5 risk factors. Now we press the OK button, and Eviews spits us out the corresponding regression model or the point estimates of the regression model, as well as other different statistics. So what we learned from this table here is, okay, the intercept, which is denoted here as C, the point estimate is 0.18, which means that 0.18% per month cannot be explained by these by the exposures, yeah, against these 5 risk factors. Yeah. The t-statistic of this point estimate 0.18 is 2.46, indicating significance on at least a 5% level. 2.46 is obviously much larger than 1.96, which is our critical value. Yeah, and here also our p-value, we see the p-value is 0.01, which is obviously smaller than 0.05. And since it's smaller than our significance level, this result indicate that our point estimator is statistically significant, which means the excess returns of the first portfolio cannot be fully explained by this 5-factor model. What you also learn from this table here is obviously all the exposures against the market factor, the size factor, value factor, profitability factor, and the investment factor are significant, yeah, highly significant. Interestingly, what we see is here the exposure against the profitability factor is minus 0.52, which means if the profitability factor increases, or if that basically means that this portfolio P1, yeah, is obviously invested, it correlates or it co-moves with the short leg of the profitability factor. On the short leg, we know there are weak firms. There are firms that have a low profitability. So obviously, if we read from the correlation here, from the covariance, which is embedded in the estimates, yeah, we see that this portfolio invests in small stocks because the point estimate against the S&P factor is significantly positive, 1.27. So it invests in small stocks, it invests in growth stocks because the exposure against the value factor is slightly negative, yeah, on the short, which means it co-moves with the short leg. And in the short leg, we have firms that have a low book to market ratio, which are growth stocks in essence, and it's actually even significantly negatively correlated with the value factor. Moreover, we see that, again, as I already said from the beginning, the correlation or the covariance with the profitability factor is highly negative. The t-statistic is minus 13.57, point estimate minus 0.52. So highly significantly negative. Moreover, it invests in firms, this portfolio is invested in firms that have a conservative investment structure, yeah, because it co-moves obviously positively with the investment factor. And in the long leg, we have firms that are conservatively invested. So P1, again, consists of stocks that are small, that are growth stocks, that have a low profitability, and that have a conservative investment structure. Moreover, the Fama and French 5-factor model is able to explain 93.8%, yeah, this is the R square, of the variation of the returns. So, which is a high explanatory power. Okay, but we are not interested now in a single equation model. We want to know how basically how does the 5-factor model perform to price the whole stock universe. So we want to have all of the stocks here, all 25 stocks. So we delete this equation, go on object, new object, and now we go to system, push the OK button. So now we have to code our system of equation here in this field. Yeah. So I already provided the code here basically in this file code for table 10, Fama and French 5-factor model. And this is basically related to the table 10 in the paper from 2015 from Fama and French, and there they use intensively the GRS test. Okay, so we can just copy and paste everything because it would be too much work to do everything now by hands. So we just copy and paste it here. So what we see is Okay, it's very simple. So we have to code it P1. Yeah, the first equation, we regress P1, the excess returns of the first portfolio is equal with C1. So C1 is now the constant in this model, obviously. This is the way how you have to write it, plus C2 times MRF, which is our market factor in excess form, plus C3 times SMB times C4 times value factor, and so on and so forth. Okay, so that's the equation for our first test asset. Second row, we have the same thing. Yeah, we just that our now C6 denotes now the intercept term for the second test asset. Yeah, and so on and so forth. C11 denotes the intercept term of the third test asset, and so on and so forth. So we see already it increases with 5. So 1, 6, 11, 16, 21. That's the ordering. And the last test asset, 25, obviously the C, the parameter estimate C121 denotes the intercept term for the last equation. Okay, so that's the model, basically very simple, actually. So now what we have to do is we have to run this model, and I told you already, we have to take into account the correlation. We have now a huge model, and you can, if you want, you can look up it in any econometrics book, or it should be at least in some advanced econometrics books. You will find it in the book from Green, for instance, how it looks like in matrix notation. But this is something that we don't need to know in theory. This is more subject of econometrics classes. This is not an econometrics classes, obviously an applied course where we just make use of econometrics for asset pricing purposes. So what we now want to do is we want to test these parameters here, C1, C6, C11 until C121 simultaneously. Yeah, and we have to take into account the correlation structure. So C1 is correlated, can have a correlation with C2, but it's also allowed to have a correlation with C6. And C1 is also allowed to have a correlation with C11, and so on and so forth. So all point estimates of all equations are correlated with each other. Okay, so because of this correlation between equations, yeah, the cross correlation between equations, and that's what we have to take into account, and that's why we have to choose the seemingly unrated regression technique that accounts for this issue. So now we go on estimate, because our system is already defined, and now here estimation method, we have to plug in here the seemingly unrelated regression technique. Okay, so this is actually a two-step estimator. Yeah, what we do first is we estimate regression by equation by equation, a simple single equation regression model. Then we use the estimated residual vectors, and using the estimated residual vectors of all these equations, we can compound the overall covariance matrix of the residuals, and this matrix we can use to compound in the second step, basically the covariance matrix of the parameters. You can also do it by an iterative procedure. This is what Eviews is doing. It optimizes, basically, it does this procedure again and again, and optimizes the point estimates and the covariance matrix. But it uses this algorithm, what you see here, but this is not so important for us to know. So what is important for you to know is it's basically a two-step procedure, but you can also do it algorithmically. Okay, but it's in principle a two-step procedure. So now we push the OK button, and then we get the corresponding estimates. So what you see here, C1, 0.18. So it's exactly the same point estimate that we get from the single equation model. So what is different, or what is slightly different, is basically later on when we implement the hypothesis test. Then it's basically when when this big covariance matrix comes into place, or is required, is needed. So C1 is as we remember, is the intercept term of the first equation. So we see t statistic indicates significance on a 5% level. Yeah. C6 is the intercept term of the second equation, point estimate 0.11, t-statistic 1.92, indicates significance on a 10% level. It's not significant on a 5% level, as you see here, because the p-value is above, slightly above 0.05. Here, C11 is the corresponding point estimate for the intercept of the third equation. 0.09 is the point estimator, and the t-statistic is 1.57, indicating that it's not significant on a 5% level and not on a 10% level either. Okay, so what we want to implement now is a basically a multiple equation test. We want to test these guys here, C1, 6, 11, 16, until 121 simultaneously. Yeah? So how do we implement this GRS test? Or I told you already during the lectures, it's a chi-square test, and the chi-square test is distributed with it has as many degrees of freedom as we have assets, or basically parameters that are part of our test statistic. Since we have 25 test assets and we are interested in testing these 25 test assets simultaneously, the intercept terms only, of course, our test statistic is distributed with 25 degrees of freedom. So we go on View, Coefficient Diagnostics, Wald Coefficient Test. And here now we have, in this field, we have to plug in our restriction, or basically the coefficient restriction that we test. And it's given here in this code. So it's basically C1 equal to C6 equal to C11 and so on until C121. And what should the value be under the null hypothesis? Under the null hypothesis, it should be 0. All of them should be 0. So let's copy this, and we copy it here in our Eviews wizard. Paste it in. So now we have formulated our null hypothesis. Yeah, all of these guys should be 0 under the null hypothesis. If we do not reject the null hypothesis, implying that we accept the null hypothesis. In this case, we would assume that this pricing model can price these 25 test assets correctly. Yeah. So let's push the OK button. What comes out? All right. The chi-square test with 25 degrees of freedom has a test statistic estimated of 83.15. So what is the critical value of a chi-square test with 25 degrees of freedom? If we want to have a significance level of 5%, we can look in a table and we see having 25 degrees of freedom and we want to have a 5% significance level, the corresponding critical value is 37.65. So whenever our test statistic is above this critical value of 37.65, we would reject our null hypothesis. And of course, 83.15 is much, much larger than 37.65. The p-value is 0.000. So what does it mean? It means that our Fama and French 5-factor model is not able to price these 25 test assets correctly, sorted by size and investment. So this is the GRS test result. Okay. So we reject the null hypothesis. We reject the Fama and French 5-factor model. This is what comes out from the left-hand side approach. So now let's close this. So now you know how to implement the GRS test for a certain set of test assets. Now let's turn our attention to testing for nested models, because this was also a big topic, obviously, of this paper. Testing nested models, so choosing among nested models and testing non-nested models. So which model to choose among non-nested models? You remember, if we test non-nested models, we have to choose a bootstrap procedure, yeah, where we create bootstrap samples via simulation. This is something that we will not cover in this course. This is something that I will cover in the forthcoming course for doctoral students and master students, which I will offer next spring for the first time. But as for now, we are interested in testing nested models. So let's test if you want to test the CAP-M against the three-factor model. How would we do that? Again, we use basically the same methodology. We go on object, new object, system. Okay, so which are the additional factors that the three-factor model has that are and that the CAP-M does not have? So the additional factors of the three-factor model are obviously the SMB factor is equal to intercept term plus C2 times MRF. MRF is the risk factor of the CAP-M model, right? Moreover, we have the HML factor, which is also a part of the three-factor model, but which is not a part of the CAP-M model. So, and we have to denote the intercept term now as C3 in parameter space, and C4 is then for the market factor. It's basically for the exposure of the value factor against the market factor. Very simple. So again, we estimate this model. We go on estimate this two equation model. We choose again seemingly unrelated regression technique, push the OK button, and this is what Eviews spits us out. So remember now C1, this is the point estimate of the size factor regression, and C3 gives us the point estimate for the intercept of the equation where we regress the value factor on the CAP-M, respectively on the market factor. So we see 0.17% per month of the size factor cannot be explained by the exposure against the market factor. But the t-statistic of 1.48 implies that this intercept term is physically not different from 0. So just based upon the size factor, we cannot say if the CAP-M prices basically, or if the three-factor model expands the mean variance frontier, okay? Because obviously the CAP-M can explain the size factor, but can it also explain the value factor? No. We see the point estimate is 0.44 of the intercept term, which means that 0.44% of the value factor cannot be explained by exposure against the market factor. Yeah, this is the part unexplained by the CAP-M. The point estimate is highly significant. We see the t-statistic is 4.05, and here the p-value also indicates significance on any level. But again, now we have to do a simultaneous equation. We have to test those point estimates, the intercept terms of both equations simultaneously, C1 and C3, yeah, if these are simultaneously different from 0. So we go on view, coefficient diagnostics again, Wald coefficient tests. So C1 should be equal to C3, which should be equal to 0 under the null hypothesis. Because again, under the null hypothesis, the CAP-M model is correct, which means that the market factor can price or can explain the size factor and the value factor, which means under the null hypothesis, adding the size factor and the value factor to the market factor does not expand the mean variance frontier. It does not increase the maximum squared Sharpe ratio of the market factor only. So if we reject the null hypothesis, what does it mean? It means that the CAP-M model, or that it means basically that the CAP-M model cannot explain both factors, the size factor and or the value factor completely, and adding the size and value factor or moving from the CAP-M model to the Fama and French three-factor model expands the mean variance frontier. Okay, it increases the maximum squared Sharpe ratio. So let's have a look what comes out. Okay, we run the test, and what we see is the chi-square test. It's distributed with 2 degrees of freedom because we are testing 2 intercept terms, and the chi-square test the test statistic has a value of 19.03. So under the null hypothesis and having a significance level of 5% and 2 degrees of freedom, the critical value is 5.99. So 19.03 is much, much larger than 5.99. Okay, so we have to reject the null hypothesis, implying that the three-factor model is in this case the correct model, as adding these two factors to the market factor only increases the mean variance frontier, and by this the maximum squared Sharpe ratio. So the size factor, value factor, and market factor together, which is the three-factor model, have a higher maximum squared Sharpe ratio than the market factor alone. This is what it means. If you would like to test the five-factor model, or if you would like to test the momentum factor, let's test the six-factor model against the five-factor model. Okay, let's delete this system here. We discussed already in the lectures. What we have to do is obviously we have to, because the only factor that is in a six-factor model included and not included in the five-factor model is the momentum factor. Yeah? So in this case, because the model under the alternative hypothesis has only one more factor than the model under the null hypothesis, it's enough to have a single equation model. Yeah? We only need the multiple equation model when testing for for nested models if the model under the alternative hypothesis has more than only one additional factor. Okay, so go on equation, push the OK button, and we run a simple OLS regression. But now let's have a look here in this data set. I don't have the momentum factor provided, right? No, I don't have the momentum factor provided. It's in a different data set. Okay, but then let's test the five-factor model against the three-factor model. So again, what we have to do is, in this case, we have to deal with a system. Yeah. So what we have to do is, what are the risk factors that are under the alternative model, but not in the null model? Of course, the five-factor model has as additional variables the RMW, which is the profitability factor, and in this case, it's actually operating profitability. Okay, we have an intercept term denoted by C1 plus C2 times the market factor plus C3 times the size factor plus C4 times the value factor HML. And the second factor that is embedded in the five-factor model but not a part of the three-factor model is the investment factor, denoted as CMA, conservative minus aggressive investing stocks. So we regress CMA again on a constant. Now we need to continue with C5 because we have already used C4 as corresponding parameter for the value factor for the RMW, for the equation for the profitability factor RMW. So C5 denotes then the parameter for the intercept for the CMA regression, time plus C6 times MRF, which is the market factor, plus C7 denotes the parameter for the sensitivity estimate against the S&P factor, plus C8 times HML. So we have now defined our system. Okay, we have two equation system, yeah, where we first regress the profitability factor on the three-factor model, including an intercept term. Second equation is the equation where we regress the second additional factor, which is the investment factor, on the three-factor model. Yeah, and also we account here for an intercept term. And again, we are interested in C1 and C5. because those guys here, C1 and C5, they tell us if the two risk factors here, these two additional risk factors of the 5-factor model, if they expand the mean variance frontier. So again, we go on estimate, we choose similarly unrelated regression technique, and push the OK button. So what we have here, we see already C1, which gives us the intercept term for the profitability factor regression. We see that 0.33% per month of the profitability factor cannot be explained by the exposures against the 3-factor model, which we see here. The t-statistic of this point estimate for the intercept term is 4.13, indicating significance on any level. Same thing for the intercept term for the equation of the investment factor CMA. We see C5 denotes the intercept term 0.1955. So we see that roughly 20 basis points per month, or 0.20% per month, of the investment factor cannot be explained by the 3-factor model. Okay. Also here, the t-statistic of the intercept term is highly significant, 3.5. So now already we know, actually we can almost jump over the next step, because we see that both point estimates are significant. So the simultaneous test would, of course, it would be mission impossible that this test basically would give us, or would result in a test statistic that would indicate that it's not significant, that those parameters are simultaneously not, or jointly not significant. But let's do it anyways. Let's go on coefficient diagnostics. Let's run the Wald coefficient test. Okay, so it's C1 equal to C5 equal to 0. So under null hypothesis, again, we assume that the 3-factor model is able to price or to explain these two additional risk factors of the 5-factor model, which means that adding the two additional risk factors of the 5-factor model to the 3-factor model would not increase the mean variance frontier. It would not increase the maximum squared Sharpe ratio. This is what we assume under null hypothesis. The 3-factor model is correct. So what comes out? So again, we remember the critical value is 5.99 for the chi-square distribution with 2 degrees of freedom, given that we want to have a significance level of 5%. And our test statistic is estimated at 41 under the null hypothesis. So much larger than the corresponding critical value. Also here, the p-value is 0, implying that we reject the null hypothesis. So this Fama and French 3-factor model cannot explain the profitability factor, or the returns of the profitability factor and the investment factor jointly. So this implies adding the profitability factor and the investment factor to the 3-factor model increases the mean variance frontier. And by this, of course, the maximum squared Sharpe ratio. So we reject the 3-factor model and we accept the alternative model, which is the 5-factor model. So thank you for your attention. This is basically what I would like to go through.